I was going through some of my notes in terms of, hey, what is like to talk about ionic bonding, covalent bonding, and all this type of sorts and molecular compounds and defining them based on the type of bonding. And one thing that stuck my mind, which you're going to see in the particular thumbnail, is that ionic bonding, is it actually 100%? And the question actually comes down to different techniques by which you'll be able to actually analyze various type of compounds and the type of bonding that exists. Now let's look back at all what you know about bonding. We talk about various atoms coming together to form compounds or molecular compounds. Now, depending on what type of elements that you have on a periodic table, you should be able to determine what is the trend in terms of ionization energy relationship with that of electron affinity, and doing those two particular analysis, you'll be able to determine that, hey, metals in general tend to react with non-metals in general to form a form of bond. Now, how strong can this particular bond be actually comes down to various analyses that chemists actually go through. One which chemists actually go through or analyze using particular technique is called the electrostatic potential mapping, and this is quite crucial because this looks at energies in terms of how you're able to bring things together to form bonds. Now, this energy is actually coming to play where you actually have a point charge, and this point positive charge is dragged around a specific compound, and by so doing you're able to see how regions are positive and negative. If you have highly electron dense regions in that particular compound, that point charge tends to be attracted more compared to regions with low electron density. And so therefore this analysis actually can be shown using different color grades. Usually green is kind of like a little bit of partial negative charge, while when you have a little bit light blue, you have partial positive charge. That's some other cases where you have spectrum of colors that exists in terms of just one particular compound. The brighter and the more spectrum that exists, either ranging from dark blue to that of dark red, you should be able to determine that that is highly ionic, versus the other case where you have just uniform colors where indeed it's highlighted to be covalent. Now, the percent of ionics interplay where we look at the percent ionic character. Now, this is shown based on the relationship with the electronegativity, where, take note, it looks at or takes into consideration the energy of ionization and that of the electron affinity. So looking at those two in a particular atom versus when another atom is reacting with that atom, you can be able to come up with the idea that, hey, electronegativity is the relationship between those two properties. And so the difference between those two properties for a particular atom actually defines that particular electronegativity. Now, this is proportional, definitely, in terms of the difference between the ionization energy and electron affinity is proportional indeed to that of the electronegativity. Now, electronegativity, sometimes you use the Pauling units to determine that different elements that you have on the periodic table are determined using the electron affinity and the ionization energy. We know that fluorine has the highest electronegativity, so therefore if you're using that in terms of any metals that you have, you can see a couple of trends happening. Now, we do have, in terms of determining that the electronegativity difference, in order for we to determine what type of bond is leaning towards. And we see that some textbook will tell you that, hey, from 0 to 0.4 is highly covalent, or 100% or non-polar covalent, while from 0.5 to somewhere around 1.7 we usually approximate it to be polar covalent, and then from that number upwards is highly ionic. So now, is there 100% ionic? According to the graph that shows the y-axis, which is a percent ionic character to that of the electronegativity, it shows a kind of a curve that is kind of, E function related, and based on that you can actually determine due to the E function that it is unlikely that you will actually have 100% ionic character for a specific compound. And that is the gist in here. The gist is how are you going to be able, using electronegativity of two atoms reacting together forming ionic compound, how much percent of ionic do we have? And you can actually see it using the electronegativity. Try this for yourself. First is look at the most electronegative atom on the periodic table, which is fluorine, and on the other side look at the least electronegative atom, which is francium. Francium is around 0.7, fluorine is around 4.0. If you subtract the numbers, you should get a number that's around 3.3. And now take note that playing the square or applying the square to 3.3, that will give you a number multiplied by negative 0.25, that will give you a number. Now that number, perform the E function to the power of that negative number, you should be able to get a number that's around 0.0657. Now take 1 and minus that number and then multiply that number by 100, you should get the percent, which is 93.4%, which is really mind-blowing, because all this while we'll be saying that, oh, this compound is ionic, this compound is not ionic. Is there a definite value for ionic and not ionic, or is it 100% or not? Even salt is not even 100% ionic. It's a spectrum that is around leaning towards 80% ionic character, that is in terms of the type of bond that is present. So in conclusion, what are we able to gather? We are able to gather that all ionic compounds are indeed ionic compounds, but there is no 100% ionic compound because of the Schrödinger's equation that is applied to the electrostatic mapping potential or potential mapping. And this mapping, which is the most recent type of method used in analyzing different types of bonds by using a unit positive charge and scanning all around particular compounds, was able to show us, or is able to show us, that hey, indeed ionic compounds doesn't hit that particular mark of 100%. Maybe in the future we'll get to that particular moment by tweaking a couple of variables here and there. You never know, but it's going to be interesting to see how this plays out in terms of you trying it for yourself with different numbers in terms of the electronegativity differences, and seeing whether at some point you will get numbers that are close to 100, or indeed what particular electronegativity difference will get that percent close to 100. Are we going to sometime in the future be able to find an element that is way more electronegative than fluorine? Only time will tell. But all the same, hit a comment down below. Let me hear your thoughts about this explanation of this particular topic involving electronegativity, and whether that, alongside knowing your concept about ionization energy and the electron affinity of a particular atom with respect to a different atom in forming bonds, will create a particular situation where we get a percent ionic character that is 100%. And let me hear your thought about it in the comment section down below. On the other hand, is it possible to get 100% non-covalent compound based on that particular assumption and based on applying that formula that was being shared with you all, and how that is going to play out in different types of elements? Is that going to be possible? Because remember, e to the power of 0 is always what? Stay smart as always and believe in yourselves.